Hello and welcome to the Decision Theory lecture. My name is Andy Collins and we're going to get straight to it. Well, we're going to talk about what is decision making. We're going to talk about rational choice. We're going to talk about uncertainty. I'm just going to introduce you to one of the paradoxes related to the modelling of human decisions, known as the St. Petersburg paradox. Talk about a bit of sunk cost fallacy and then some other concepts. And then we'll wrap up this video. So, what are common decisions? You might have some trivial decisions like, what should I wear today? What should I eat for dinner? Etc, etc. And there might be more complicated ones in life, like, what shall I do as a career? Should I invest in a new outfit for a job interview? Especially if you're unemployed at the time, that might be quite a large expense for you. So you might want to consider not buying an outfit, but that decreases your chance of maybe getting the job. So, etc, etc. There's all kinds of different decisions that we face. So, what is decision making? Well, decision making is a process. It's a process where you've got more than one possibility, more than one choice that you can choose from. The decision maker can form some expectations about the future outcomes and the events that may occur from each given choice. And there's consequences associated with those choices that can be evaluated in a subjective way. Okay, so for example, if I'm going to decide what I'm going to eat for dinner, I might decide between having a salad and I might decide between having a burger. So I have more than one choice there. The expected outcomes are, as fits, is that I'm going to eat the burger or the salad. And there's certain consequences from that. So the burger is not going to help my weight situation, probably not the healthy choice, whereas the salad will. But then again, I'm going to enjoy the burger more than I am the salad. So I've got to weigh in all these different factors that come into evaluating the different options. So how do we decide? Well, there's a lot of different techniques out there. We're going to touch on some of them. We're going to touch on one particular type one. And just remember, one crucial thing about decision making is decision outcome isn't necessarily a good indicator of decision quality. So, for example, if you decide to go to the university and you're going to walk across a major highway and you don't get hit by a car or a truck, doesn't mean that you've made a great decision, even if it does mean you get to school quicker. There's all those extra elements that you need to consider. There's elements of like there's a risk that you're going to be hit by a truck. It's that you're paying for that risk with your life potentially. And you need to take all these into account. So a good decision or decision quality is one that really takes into account these uncertainties and all these extra elements that come with it. So rational choice is when we do things that maximize our happiness. So a rational player is one that chooses an outcome or event that will maximize their happiness. And this happiness can be somehow quantified in a function called the utility function. Okay, and what we usually represent this by is the U, the utility function, and then there's some outcome. So what does the utility function allow? The utility function allows us to somehow compare different outcomes. So one outcome might be I get $1 million. The other one is I might get to fly to the moon. Quite hard to directly quantify, but I'm guessing my utility of flying to the moon is better than my utility of having $1 million. Okay, so when we model decisions, we tend to assume that the people making decisions are rational decision makers. Now, this isn't always true. Humans are notoriously irrational. You give the identical product to an individual or some individuals, and one is lower price than the other one. You would expect them to always take the lower price one. However, that's not always the case. There is always some individuals that will pick the higher priced one given the two choices. This is an experimental conditions. Somehow they feel they're getting more by going for the more expensive version. Okay. Now, in some cases, that is a rational choice. So, for example, recently I wanted to buy a product from Walmart. which was $1 cheaper, so it was $3 as opposed to $4 than my local supermarket. Now I could choose to still buy it from the local supermarket. Why would I want to do that? Well, Walmart can be very, very busy. It can be very difficult to return a product if there's a fault, because the customer service lines are problematic. Whereas I know this supermarket that I could go to actually will be very good and have a great return policy. So that might be a decision I take in there. But the reality is, for that amount, and given the hassle of having to return it, I probably don't care. In which case I'm going to choose the $1 cheaper version at Walmart. So just because I've chosen an action or a direction from the decision I was trying to make, doesn't mean I'm going to get the outcome I want. Just because I choose to gamble my money in a casino doesn't mean that I'm necessarily going to win. As such, sometimes when we're thinking about decisions, we need to account for uncertainty. And what do I mean there? So what I'm talking about is the idea that there may be multiple outcomes because of our decision. If I go to the casino, I may win millions of dollars, or more likely, I'm going to lose all my money. So when I'm weighing that action, that potential choice in my decision making, I need to account for the fact that it could be that I lose the money or I win the money. Now, how much I'm going to do that depends on the probabilities I expect those different outcomes to have. So I may make a decision to leave the house. Now, there is a chance that a satellite is going to fall from the sky or a meteorite and hit me when I walk out of my door. But I think the probability of that is pretty low. So even though the consequences of that are pretty bad, I'm quite happy to ignore that. So the way we judge this kind of uncertainty is we times the probability by the utility, and that gives us a new value. And if we add up all the possibilities, those values of the probability times the utilities up together, that now gives us what we call the expected value of the utility of the action that we have chosen. Okay, so I might go to Las Vegas and think I might lose $1,000 with a probability of 99. Then I might win $1,000 probability of 1. Now, 99 times 1,000 is 999. That's minus plus 1 of 1,000, which is 10. So you can see I'm going to end up in quite the negative there of the expected value of the decision to go to Vegas if I only expect to win $1,000, but most likely expect to lose $1,000. So we got this nice little formula at the bottom here, which just summarizes what I've said in terms of the expected value of the utility. Now, I just talking about the Las Vegas example, and I equated money to utility, but that's not necessarily true. And the easy way I always give to explain this is to consider this. If I turned around to you and said, I may give you $0 or I may give you $1 million, you're probably going to be a little bit upset if I decide not to give you the $1 million. However, if I turn around to you and say, I might give you $1 million, but I might give you $2 million, you probably still might be upset if you don't get $2 million, but not as upset. So even though the same difference is there of $1 million between 0 and $1 million and 2 million, your care starts to dwindle. Okay, so if you turn around to me and said, Andy, I'm going to give you $1 billion, and I go, okay, that's great. Or you said, well, I might give you $1,000,001. I'll be like, I genuinely don't care, right? $1 billion and $1, it does not matter to me. Okay, I'm quite happy to take the $1 billion. Okay, so the way we can actually prove this, when this idea, or not necessarily prove it, but we at least show some weaknesses with our model so far, is to show this problem of not accounting for the difference that people have compared to what they actually see the utility of, what the actual monetary value is is we can look at some paradoxes. So we're going to look at the St. Petersburg paradox first. Now, the St. Petersburg paradox is just from a game. And what this game is a game of chance. I'm going to let you flip a coin until you get a tail. So if you flip the coin and get a tail, okay, nothing happens. However, if you flip a head, and you keep flipping heads and don't flip a tail, then what I'm going to do is, until the number of heads you manage to flip, I'm going to give you 2 to the power of that. So if you flipped 4 heads, that's 2 to the power of 4, which is 16. So I'll give you $16. Okay. So the question comes up with St. Petersburg paradox: how much are you willing to pay to play that game? How much? Given that much there, the odds there, you might get $1 if you flip. You only flip a tail. Actually, I take that back. You get $1 if you flip a tail, because it's 2 to the power of 0, which is 1. So you might get $1, $2, $4, $8, $16, $32, $64. So the question is, how much are you willing to pay? Have a little think about that for a second. Okay, so let's have a look at the mathematics on this. So, what is the expected utility? Well, we've got a half chance that you're going to flip a tail. You're only going to get $1. You've got a half times a half chance, so that you actually flip only one head. So you flip a head and then a tail, so you get $2. And we can do this over and over again and go through all the possibilities. Which we get is 0.5 plus 0.5 plus 0.5, which tends towards infinity. I've said it equals infinity, but infinity is not a number, so there's a tendency towards infinity. So this game I've just offered you, you're going to get the expected outcome is staggering, absolutely staggering. More money than there is in the world. Okay, is the expected outcome here. So you really should be prepared to pay me everything you've got to play this game. But I'm pretty certain that no matter what number you came up with to say earlier to play the game, it wasn't everything you got. Okay? So why is that the case? Why aren't you prepared to do what the mathematics says? Well, mathematics is just from a model about us and how we treat things. And this idea that money equates to utility doesn't work. And this is what the St. Petersburg paradox shows us, is that if you just equate money to utility, it doesn't quite work out. Humans tend to be risk averse. Yes, there is a chance that you're going to win all the money in the world, but it's like a very, 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 very small chance. And it's like, well, I'm not particularly happy with those odds. Okay, so it's not the only paradox that we face. There's the other ones in there when it deals with utility theory, because it's that interface between mathematics and human behavior. So another famous one was Alias's paradox, which showed that humans do not have a simple utility function. We'll talk about that in a later lecture. And that led to the development of the prospect theory as a way to counteract Alias's paradox. But my favorite paradox is, which is connected to human behavior, is Braze's paradox, which is, in certain circumstances, you can show that adding more roads to a network, adding more roads in a local community and whatever else, can actually lead to more congestion. And this is to do with driver behavior, which I thought was quite funny, because your instincts there is like, well, actually, if we add more roads, that should make congestion more relieved because there's more roads for people to go on. But it can actually make things worse. We've been a little bit critical just now of the approach of mathematically representing utility and how that utility might feed into human decision making. However, there are some things that I think that the utility theory does get right. One of them is that it doesn't consider past decisions. It doesn't consider past costs in the development of the utility itself. It's always about what's going forward. And this is something that humans tend to have a problem with, is what's called the sunk cost fallacy. So we tend to account for or look at what we spent in the past, even though we spent it in enabling our future decisions. So one example is, you may have spent thousands of dollars on a master's degree, but if you don't think it's going to get you where you want to go in your career, or it's not something you're particularly enjoying and you don't think you really want to go to the end of it, then just because you spent thousands of dollars is irrelevant to that decision. Okay, you have that debt regardless. If you continue, you have the debt. If you don't continue, you have that debt. Now, the masters may give you a better job in the future, which may enable you to pay off that debt, and that may be part of that decision now, is that in your world reality you have debt on with you. Okay, so to me, it's nice that it doesn't take into account that the fact that what's happened in the past stays in the past. Okay, so let's just talk a couple of examples. So one classic example would be the talk about sunk cost fallacy. Is there may be a team in an organisation, they were developing a project and they spent a lot of money on the project, but they realised that the finished project is going to be worth less than what more they're going to actually spend on it. So they've already spent the money, but it may require, to say, the product is $1 million. That's what they're going to get for it, and they still need to do $2 million worth of investment. Just because they spent $10 million doesn't mean they should spend the extra $2 million. Okay, going forward. So there would be a wise thing to cut that decision out. Another classic one is that people, when they sell an item, they try and get the amount they bought it for, because they want to recoup their money. They've already spent their money. This was a big problem after the 2008 housing crisis, because people saw their houses at, being worth at what they were at the peak of the market. But yeah, that's what it was in the past. But that's not reality now. That even to this day, the housing market hasn't truly 100% recovered from that crash. But people saw that. They saw their house at some point was worth $1 million. So they felt that they could try and, or should be able to sell their house for $1 million. But no, it's no longer the case. The market has changed. What was in the past has gone. So let's talk about one example. One example here was Ford. Ford chose to stop investing in one of the new product lines, even though they spent over probably about almost $3 billion in this new car. When they realised there just wasn't a market for it. There just wasn't a market for this type of car out there, so there was no point in pushing that forward. Secondly, also you could argue that Japan chose to surrender in the Second World War, realizing that there's going to be terrible future bloodshed that carries on. Now there was a lot of Japanese lives lost, and they could have kept on, or obsessing about that. But they chose to look for the future, look to what was going to happen in the future to the populace, and make the decision to surrender. Okay, I'm just going to now touch on some other concepts connected to surrounding, but connected to utility theory, just because I wanted you to have some understanding of these concepts. Okay, and in a later lecture we're going to be talking about in more detail about utility theory itself. So one of my favorite concepts is the Pareto Principle, which is 80% of the objectives can be achieved with 20% of the means. So when you're starting a project, especially a research project, that 20% of the insight or the development or whatever the critical piece of the project is achieved with 20% of the expenditure, and you get 80% results. And it's when you're trying to get up to that 100%, that's what can really suck up the results. This is a classic that happens in academia. It's usually 20% of students take up 80% of a lecturer's time. Okay, but similarly with the research project and the class, it's not suggesting that you get rid of those 20% of students. It's just accepting this is going to be the case. Okay. So why is this important? Why is it saying this? Well, sometimes we're making a decision, you're making that decision of, hey, How much energy should we go in it? Should we keep on trying to go forward to get a slightly better solution than what we got? And if you've already got a pretty good solution, then you could end up wasting a lot of energy trying to move forward to get to that better solution that you're requiring or wishing to achieve. Which leads me on to the next concept, which is optimality versus sufficing. Sufficing is this idea of you've attained some kind of solution, or you've come up with some course of action as your decision that suffices. It satisfies you to achieve your objectives, but it might not be optimal. There might be a better way of doing this. A classic example for this would be that yes, if you could invest in the stock market, you could look at the different stocks out there and try and learn the market and go and see if you can get a 4, 5, 6, 7, 8, 9, 10, 20% return on your money. Or you could just invest in mutual funds, which effectively do a spread across the market and are already doing that for you. Yeah, you might only end up with an average of 4%, but you haven't had to invest all that time and the dangers that come with investment by doing that. So you may be able to enjoy your life more. So sufficing is when you take in a acceptable solution, even though you might not know, it might not be the optimal solution. Now, what we've been touching on so far with these is with the sufficing the Pareto Principle, is this level of uncertainty. And it's not just uncertainty about what the outcome is going to be, it's even uncertainty about what potential outcomes are, what potential ways you can actually handle a particular problem. And that's one of the crucial things about decision analysis, is taking into account that uncertainty, especially in complex environments. Now, the concept of bounded irrationality really allows us to take this into consideration. It's really this concept of, what decision you might make may not actually seem rational to someone outside, but when they realize how much limited information you have, given that limited information, it does seem rational. Okay, it does seem like a rational decision to move forward with what you're doing. Okay, so for example, you may know that a particular route is always prone to having traffic accidents in it, and then you've got a friend coming to visit you, and you find out that they've taken that route, and you're like, well, oh, okay, why did you do that? So, well, they said I looked at the map and this looked like the most sensible way to get to your house. And say, well, yeah, but there's always accidents there. And so, well, I didn't know that information. So I made what was the best decision available to me. But now I'm stuck in a major traffic jam, and I have to accept that I'm going to be late to the party or whatever reason that they were invited to come around your house. So, like I mentioned, bounded irrationality probably is our natural state, and it's a concept that's very important, I think, in terms of modelling human decision making, because we probably don't know all the alternatives that are available to us. Yes, and with the combination of the Pareto Principle, yes, we could spend a lot of time and energy trying to find different alternatives to any decision we're making, but we've wasted that energy. We probably, in the 20% of effort, come up with probably the best alternatives that are viable, and that extra 80% of effort is just producing some extra alternatives which may or may not be viable or may be optimal that we haven't come across. So I think when it comes to decision making, we need to take that into account, that we're not going to have all the information that we require. The other crucial thing is what we call finite causality, which is the idea that nothing is ever infinitely good or infinitely bad. There's no extremes in that sense, and as such, given this there is this bounding point over there, there's sort of that we are facing, and that bounded rationality that we have, and it's never going to be an infinitely bad or an infinitely good decision. that we make, it sort of like gives us some comfort in decision-making process. But also, more importantly, the infinitely causality, finite causality, is crucial to us because it allows us to put some constraints into the mathematical models that we produce. Here are a few references from the lecture.